Physics, the very first topic you encounter will be kinematics, which sounds off-putting right off the bat, but break down the word. Kine is the root word for motion. So kinematics is the study of motion. You've seen kine in kinetic, as in kinetic energy, and the energy an object has because of its motion, or perhaps kinesiology, study of human motion. So one key distinction you'll need is to understand the difference between velocity versus acceleration. Now these words, and you'll discover in physics that words get used in the physics context that might be a little bit different than how you're used to using these words when you use them in everyday conversation. So there is a verbal component to physics as well as the math component, because along with understanding definitions, you will also do calculations to describe the object's motion. For example, if you know the object is moving at a constant velocity, you can figure out after a certain amount of time how far it's traveled. Or if you know an object is starting out with a certain velocity and then it accelerates after a certain amount of time, you can also figure out how far that object traveled. So over the course of time, you'll get good at doing these, solving these types of problems. But let's start with the key definitions. So in the physics sense, the definition of velocity is the rate of change of position. Now notice I don't say over time, because the word rate implies that something is happening over time. So again, if I want to state this as in physics symbols, it looks like lowercase v with the arrow equals delta. The delta is the uppercase Greek letter delta, which looks like the triangle. So delta x, that's the change in position, divided by delta t, change in time. Now, why do we even bother with these deltas? Why don't we just say it's distance over time? Okay, so there's a deeper reason for this, and I'll circle back to that at the end of this video. But the key thing here to remember is you will see deltas, those triangles, a lot in physics, and that means you always take the final value and subtract the initial value. So the change in position means find the final position of the object, subtract its initial position. Sometimes these values can wind up being negative, and that's okay. Now, the same thing applies to delta t for the change in time. You could say, well, isn't the time just the time that's gone by? And in most cases, yes, because if we take the final time and subtract the initial time, most people would start time at time equals 0 seconds. So the change in time would just be whatever time you stopped at. But in physics, we do not want to make any assumptions. So we do not want to assume that the initial time where you started the clock was at 0 seconds. What if you started the clock at 1.5 seconds or something? So hence we just cover ourselves by using the delta. Okay, so that's the first definition. Velocity is the rate of change of position. The second definition, acceleration is the rate of change of velocity. So it looks like lowercase a with the arrow equals delta, lowercase v with the arrow, divided by delta t. Alright, so I should explain what these little arrows over the letters mean. And what those arrows indicate is that quantity, whether it's v or a, velocity or acceleration, those are what we call vector quantities. vector quantities have a direction, not just a size. So for example, if I say my velocity is 50 miles per hour, I have to specify the direction. So 50 miles per hour north. I would be correct to say my speed is 50 miles per hour, because speed is what we call a scalar quantity. I don't need to specify the direction. Similarly, for acceleration, I have to consider the direction of the acceleration. Now that might sound, maybe that sounds obvious or not obvious, or it's a little odd to you why we would specify direction, but as you will come to see over time, we don't just specify direction with the cardinal direction like north, south, east, west, or right, left, up, down. In physics, typically we will assign one direction as the positive direction. So for example, I could say I want up to be the positive direction. Well, that implies that down, since down is the opposite of up, that implies that down is the negative direction. And so when we start to do calculations, that becomes crucial, because, you know, as you know from doing your math class, if you mess up with a plus or minus, positive or negatives, it will result in an incorrect answer. So same thing goes for physics. We gotta pay attention to the signs, and especially when you are dealing with what we call the vector quantities, that's kind of a hint to you that you gotta be really careful about direction when you see that little arrow over the quantity you're working with. Okay, so let's take a look at applying these definitions. Well, the first one for velocity, that basically generates the only equation you'll need to use for velocity. Now here's the big warning. You can only use this when the velocity is constant. That means you're on cruise control. You're not changing the direction that you're traveling in, and you're not changing the speed. If that's the case, then you can just plug in numbers, right? There's three quantities: velocity, change in position, which is also known as displacement, the delta x, and then the change in time. So in order to solve, you need 2 out of 3 of those. As long as you have 2 of them, you can solve for the third. So an easy way to represent this is to draw those 3 values. Instead of the v with the arrow equals delta x divided by delta t, I put that in this triangle device. So that way you don't have to memorize 3 separate equations. You don't have to remember 3 variations of the same thing. You just remember this triangle, and then whatever quantity you want to solve for, you just put your finger over it, and then you see how to find it by plugging in the other 2 values. Alright, so again, just make sure the only time you use this is when you know for sure that the velocity is constant. And how you know that? Well, you'll have to read the question very carefully. It should tell you that. There should be no mention of an initial velocity and a final velocity. And if there's not a constant velocity, that implies that there is an acceleration. Does that make sense? If something's not moving along at always the same speed in the same direction, that implies that it is in fact accelerating. Now here's the word of warning for physics class. Acceleration in physics means it could be speeding up, or it could be slowing down. Physicists consider slowing down an acceleration in the negative direction. That might sound a little odd, but if you think about it, if you were going in the forward direction and you slam on the brakes, you're going to slow down even though you're still traveling forward, but you're accelerating in the backwards direction. Okay, so basically the acceleration is in reverse in your reverse direction, so it's eating away at your speed going forward until finally you come to a stop. Now, the third way you can accelerate in physics is you could change your direction. So if you are going at the same speed, but you start just going around in a circle, like driving around in donuts in the parking lot, you are in fact accelerating, even though your speed is constant, because your direction is also changing at every point around the circle. All right, so just remember, acceleration for physics, speeding up, slowing down, changing direction. So now, whatever you do, don't tell your parents you're in the accelerated program at college because you're going to slow down and it's going to take you 6 years to get through college instead of 4. They won't be really happy if you use that definition of acceleration for slowing down as you make your way through college. But in any case, let's take a look at how we represent acceleration as the formula. In this case, it's lowercase a with the arrow equals delta lowercase v with the arrow divided by delta t. Alright, so that's the definition. And from that, we get 3 equations that you absolutely just have to memorize. So, I'm telling you up front, just memorize these equations. I know some of you are going to say, well, hey, I get a reference table. I don't need to memorize it because it's going to be on the reference table. And the answer is, actually, you do want to memorize it because you don't want to spend 1 calorie of brain energy trying to find this equation on the sheet, number 1. Number 2, if you are under that type of pressure, say you're taking a test, you don't want to be fumbling around trying to find the equation or make a small mistake with the equation, and it's just easier for you if you just memorize them right off the top. Okay, so let's look at these 3. So the first one is velocity equals the initial velocity plus the acceleration times the change in time. So it looks in symbols like lowercase v with the arrow equals lowercase v with the arrow subscript 0. The 0 stands for time equals 0 seconds, so that would be the initial velocity at time equals 0 plus acceleration times, or lowercase a with the arrow times delta lowercase t. Okay, so that, if you look at it, is just a rearrangement of the first equation I gave you, which was the definition for acceleration. If you plug in initial velocity or final velocity, which would be just the v minus initial velocity, if you plug that in on top. Okay, the second one, now it starts to get fun. It's the change in position equals the initial velocity times the change in time plus 1/2 times the acceleration times the change in time squared. So in symbols, it looks like delta x equals v with the arrows 0 times delta t plus 1/2 a with the arrow times delta t squared. So key points here, the delta t, the second delta t is squared. That's the only part of that that's squared. You don't square the acceleration and you don't square the half. It's just referring to the time. Okay, the second thing to remember is don't forget that second term, the 1/2 a delta t squared. That's again where students mess up and just forget about that second term. But if you notice that if you forget that term, that implies that you were dealing with a constant velocity, right? Because the a is 0, that second term goes away. But the reason we're going over this is because now we're dealing with a constant acceleration, so we need to include that second term. And just also remember, it's just not a times t. People think they can sub in a times delta t because they just rearranged the definition of acceleration, but that doesn't work. Okay. So that's the second one. The third one, this is really fun. We get velocity squared equals the initial velocity squared plus 2 times the acceleration times the change in position. So in terms of symbols, it looks like lowercase v with the arrow squared equals lowercase v with the arrow subscript 0 squared plus 2 times acceleration times lowercase a, the arrow, times delta x. Okay. So now, another key thing with these formulas is no matter what, don't start changing the plus signs to minus signs. As long as you keep straight with all the variables that you're plugging in, that's where you're going to have either plus or minus signs. Do not change the plus signs in these equations. Okay. All right, so you're going to memorize those 3 equations. Now, if your course also includes graphs, you need to just memorize these 3 rules for the graphs. The first one is the slope of the change in position, delta x, versus delta t graph. So that means the delta x would be on the vertical axis and the delta t would be on the horizontal axis. The slope of delta x versus delta t is the velocity. That means whatever value you get for the slope of the line, if that's positive, that means the velocity is positive. If the slope is negative, that means the velocity is negative. Okay. And if the slope is 0, that means the velocity is 0. All right, that's the first rule. Second rule, the slope of the velocity versus time graph is the acceleration. Same thing. If that slope is positive, then the acceleration is positive. If that slope is negative, then the acceleration is negative. If that slope is 0, then the acceleration is 0. So that's the second one. So the first 2 involve the slopes of graphs. Make sure you check what's on the vertical axis, because that makes all the difference. Okay, the last one is probably not intuitive, but it's important for you to know this one also. So the area under the graph of velocity versus time is the change in position. So what that means is you would look at your graph of v versus t and shade in the area from the graph line to the horizontal axis. And you would find the area of whatever that shape is. It might be a triangle, rectangle, trapezoid, or parallelogram maybe. Anyways, find the area of that, and that is in fact how the change in position for that object. Now, it can turn out where you have an area on top of the t-axis, meaning the horizontal axis, and then you might have an area that goes underneath the t-axis. If that's the case, the area that's underneath is considered negative, so you would subtract the negative area from the positive area, and you'd wind up with a value. And whatever that number is, whether it's positive or negative, that is in fact essentially how far the object traveled, its change in position. Okay, so for the motion graphs, we have to remember about 2 slopes and 1 area. Now, finally, here's a couple more things that you should know that I wouldn't say they're not as important, but they are sort of, well, they come up less often. So another key definition is the difference between distance and displacement. So distance is the total length of whatever path something travels. So let's say you walk out to your front door, you turn right, you walk down to the end of the block, turn right again, turn right again, turn right. You go all the way around the entire block and come back to your house. Well, what's the distance you traveled? The distance is 4 blocks because you just went around in a square, right? But the displacement is the length from start to finish. And since you ended up the same place you started, your displacement is 0. It's nothing. Okay, so that's a key definition for you to know. Last one is average speed and average velocity. So average speed is the total distance divided by the total time. Sometimes people will think, if it's the average speed, I should find a bunch of speeds and then take the average of all the speeds, and don't do that. Okay, so similarly, average velocity is the total displacement divided by the total time. So again, if there's different segments of your trip, do not take the averages, don't take all the velocities and then find the average of a bunch of numbers. That's not how to solve it. Take the total displacement, divide by the total time for the trip, and that'll be your average velocity. Okay, but in all honesty, those types of problems, you should not be dwelling on them. You're going to spend a lot more time working on those 3 that I told you to memorize. Now here's the other thing you should know about it. Just if you practice enough, you're going to wind up memorizing those by default, just because you're going to use them repeatedly and it'll just go into your brain. But so that is actually the key for kinematics is practice. Okay, so I'll give you one more sort of punchline for this, which is the big culminating subtopic for kinematics is something we call projectile motion, which simply means, for example, throwing a football in an arc, throwing a 3-point shot in basketball, firing a cannon if you partake in such things, or even actually firing a bullet from a gun. In all of these cases, the object that gets fired or thrown travels in an upside down parabola. Believe it or not, it might be super shallow, but it is parabolic. It's not semicircular. Okay, and for those of you who care to kind of look ahead or are confident and can jump through all of this on your own, the key thing for projectile motion is remember that the motion in the x direction, meaning horizontally, is constant velocity. But the motion in the up and down direction is subjected to constant acceleration. So that means to figure out what's going on in the horizontal direction, you can use that triangle equation I showed you. But to figure out what's going on in the vertical direction, you have to use one or more of the 3 equations I told you to memorize, and the ones you need to use depends on the information you're given. Now you will also need to apply trig definitions, sine, cos, tan, so, ka, toa, but I'll assume that you've done that before, and of course you're going to use your calculator to figure those out. So that's how you deal with projectile motion in a nutshell. But that deserves a whole nother lesson unto itself. So finally, remember I said I was going to talk to you about why we spend so much time with the deltas in physics? And the reason is, I could actually summarize everything I just said with the triangle equation, those three equations I told you to memorize, and the whole business of slopes and graphs. I could summarize that in simply 2 definitions if we know calculus. So if you know the language of calculus, it's a lot easier. It's just v with the arrow equals dx by dt, and acceleration, a with the arrow equals dv by dt. You can say, well, that's awful convenient that just these 2 little equations kind of encapsulate a whole bunch of formulas and ideas about graphs. And the thing is, calculus was a language developed by Sir Isaac Newton to talk about physics. So it's not really a coincidence that the language he developed is a succinct way of explaining or describing different concepts about motion that he wanted to communicate. Okay, so I guess my point there is like people figure that calculus is kind of the toughest subject you'll ever take, but it's really just the language that Newton decided he needed to develop in order to communicate about physics. So the two are really married together. Okay, so that's my summary of kinematics. So essentially there's four formulas you should memorize, 3 ideas about graphs that you should memorize, and then just the definitions, for a couple of definitions for constant velocity, constant acceleration. Now here's the other thing. The assumption is that at the algebra-based physics level, you're only going to deal with constant acceleration. You're not going to deal with non-constant acceleration. That you can wait until you get to calculus-based physics for. So please comment with any questions you have or any additional topics you'd like me to speak about, or any clarification that's needed. All right, thank you so much for listening. I hope you're enjoying physics, and we'll see you the next time.